Okay. So okay. So anyways, yeah. Okay. So let's begin. Yes. So today we're going to go through basically logistic regression. Today's session will be quite short. Can I just get a mic check from someone? Can someone tell me that they hear me loud and clear?
Yeah,
Yes.
you like.
Yep.
Okay, sounds good. So yeah, today we'll be going through some logistic regression stuff. This is actually just building up from linear regression, which we touched on 2 weeks ago now. Yeah, two weeks. Actually, no, 10 days ago. Yeah, 10 days ago now. Sorry, no, not 10 days. 12 days. What am I saying? Yes, 12 days ago. Anyways, yeah. So just to begin, let's just get some admin stuff straightened out. Amadeus released or sent the link rather on the group the Kaggle challenge that we want you guys to take part in. So basically, the main thing that you do in that is time series. So you use time series. So we want you guys to really uh, try your best and really try to explore some time series models. And the deadline for that project is October 3rd. That is a Saturday, 11:59 p.m. So yeah, so we want you guys to just get that done by Saturday, 11:59 p.m. This is not to put any pressure on you guys. If you guys have some special sort of reason why you cannot make that deadline as we get closer to it, please do let us know, but like slightly in advance. Um, we do want to see effort really. So those who do not submit, you guys are considered to be like on a bit of a probationary period right now. So obviously we're looking for that sort of that interest, that ability to juggle school and this. So it's quite important, right? We're not looking for results or anything great. So we just want to see some degree of effort and exploration. Now, anyways, I think I've drawn down about that long enough. Let's begin, right? So today's concept is logistic regression. And oh yeah, just one more thing. Today's thing is going to be quite short because, or at least I think it's going to be quite short. The reason is because we don't want to take too much of your time over the span of a week. And on Thursday, we're going to have that resume talk that Sakti and Co have arranged for you guys, the directors of the machine learning department. So yeah. Anyways, let's resume. So there's two types of learning. We already recapped this. Just recapping again. So supervised learning and unsupervised learning. Supervised learning is the type of learning with a label. Supervised learning without. um, so the focus for training wing is supervised learning. We talked about there are two types of problems. There are numerical predictions and then there's classification problems. We mentioned that at the start about 10 days ago, right? I'll just say 2 weeks ago. Yeah, 2 weeks ago. Today we're going to be talking about classification problems. That's our focus for today, right? So, okay, I really need to switch off these notifications. My God. Okay, wait. Ay, ay, ay. Actually, you know what? Never mind. It looks like I won't get many more notifications. Anyways, yeah, fine, sure. Yeah. So today we look at classification problems, and one funny example is this 1 minute clip that I found really funny. So, um, should yeah. So this is a video of classification problem being handled in
Ready.
quite a funny manner. So I don't know if
Please
you guys
go
can hear.
ahead.
Can you guys
What
hear?
will you say if I told you
Is
there
the
is an
audio?
app on the
You guys
We're
market?
hear?
past that part. Just demo it.
Yes, can hear.
Okay. Let's
Okay.
start with a hot dog. Oh shit!
Yeah, it works! Oh, motherfuck!
Huzzah!
Jin Yang, my beautiful little Asiatic friend. I'm going to buy you the palapa
Yes,
of
just
your
keep in mind
life.
this is
We
meant
will
to be a
have
bit of a
12
comedy show
posts,
anyways.
braided palm
Yeah,
leaves.
just give it 30 more
You'll
seconds.
never feel exposed
You
again.
guys can
I'm gonna be
see
rich.
what I'm coming
Fuck you,
to with this
Guilfoyle.
video.
Do pizza.
Yes, do pizza.
Yeah.
Okay. Pizza.
Yeah, so basically
Not
this is
hot dog.
what logistic
Wait.
regression does at a very simple level. So yeah, so anyways, with that note, the show by the way is called Silicon Valley if you guys want to check it out. So anyways, logistic regression on a more serious note can be used to identify stuff like if a tumor is cancerous or malignant. So that's one really kind of common use case example given in many machine learning tutorials. So logistic regression is more commonly used in linear regression, mostly because linear regression you have for numerical classification, numerical predictions, you have much better ways of predicting than linear regression. For logistic regression, it's one of the better ways of classifying. So yeah, logistic regression is quite commonly used. So when you think about it, logistic regression provides like direct outcomes. So that is like a result. So it's either this or this. But in fact, that's not what we do in logistic regression. That is what you commonly associate with it. But logistic regression, what we're essentially looking at is the probability that you get. So for example, for given these circumstances, these situations, what is the probability that it's a certain kind of outcome? So that is a probabilistic view of things. This differs from a straight classification problem. So technically, if I said classification, you would just get a 1 or a 0, or a 1 or a -1, or something like that. So you're just putting it straight into a band. Logistic regression is a probabilistic thing. So for example, I would say 0.97. That would mean there's a 97% chance that the label of the situation is 1, something like that. So that is what logistic regression is. Um, okay, so logistic regression, just to show you, is you can think of it similar to linear regression in that we do have a line, but instead of a line where you're kind of predicting uh, the output based on where the input lies on the x-axis, right? What you're actually doing is the line actually acts as something called a decision boundary. So this graph here that you see, right, is um, is basically showing you like, sorry, one moment, yeah, sorry, yeah, so basically what you have here is an xy plot where these dots are plotted on the graph, right? These two sets of dots, the ones on top and the ones below, they represent two different classes essentially. And sorry, let me just admit the person. Yeah, okay, so these two represent two different classes. So when you see this line over here, it's attempting to separate these two classes, and it's doing a very poor job, by the way. But yeah, so over here what you have is a decision boundary. So the one that is on top of the black, sorry, one second, let me try to annotate if I can. Sorry, one moment. Yeah, okay, sorry, yeah, okay. So anyways, so yeah, so anything that is on the left side of the decision boundary will be considered one type of class. Anything to the right side below the decision boundary will be considered a different kind of class. So this is kind of the idea of logistic regression. So let me just show you how we would work that out in numerical terms. If you remember correctly from the last time, right, I was talking about a hypothesis with linear regression, and I said if you have two features, let's say x1 and x2, and then obviously you have some sort of decision in this case. So before it was, we used to just say y, and y could be any sort of member of the real numbers, right? But in this case, y will be constrained to some sort of class sort of thing. So it'll be y where y can take the values of 0 and 1, or -1 and 1, something like that, or maybe even 1 2 3, something like that. Okay, so for the sake of simplicity, let's just take it as two classes, right? So let's just take y can take the value of 0 1, and let's take x1 and x2 as some sort of random feature. So a common data set that is used is this iris data set, which deals with I forget the exact label of it, but anyway, so it has, you have details about flowers and stuff like that. So like petal width and sepal width. Okay, yeah, something like that, right? So now you have these two inputs and you're trying to classify it as, let's just say, some type of flower. The one could represent a certain kind of flower and the 0 can represent a different kind of flower. So if you looked at the graph, right, so let's just plot this as a graph. uh, let's just say that this is the sepal width. By the way, you guys have to sort of divorce yourselves from the idea that every graph is this sort of y versus x, where y is a function of x. In these graphs that I'm drawing here, y and x are not dependent on each other in any way. Oh, sorry, y is not dependent on x in any way. This is just for representation purposes. So the sepal width is actually not dependent on the petal width. This is just, you guys need to sort of get away from that idea from high school and stuff where the graph is always y is a function of x. This is not the case. Anyways, so in this representation, right, let's just say that you had a bunch of points here. So let's just say uh, 1 is represented by x and the 0 is represented by o. Okay, so let's just call this flower A, flower B. But on the graph, for simplicity's sake, we can represent it with a circle and a cross. So I would, for example, let's just say that for hypothetical sake, there was a bunch of x's here, and there's a bunch of zeros here. Okay, so here you can see there's a clear sort of separation of the two classes. So these have a high petal width and low sepal width, and with this it's the opposite case, right? So a decision boundary that you would draw might look something like this. Okay, so that means that anything on this side is considered to be a flower A, which is the type X, and anything on this side is considered to be a type 0. So what is this line when you think about it, right? Remember what we were talking about with linear regression is the hypothesis function that we have, which is h theta, and it takes in some input x, is equal to some theta 0 plus theta 1 x plus, sorry, theta 1 x1 plus theta 2 x2. Do you remember this? So um, in this case, we can sort of represent that with this line here. So yeah, so let's just, okay, let's just for the sake of this, let's just say theta 1 x1 plus theta 2 x2, right? So uh yeah, sorry, just give me a moment. Yeah, so then the intercept over here is 3. So the theta 2 is equal to 3 plus theta. Okay, so let's just say that it's like let's just say the decision boundary is something like this. So theta 1 plus theta 2 minus 3 uh, is greater than or equal to 0. So this is like some sort of decision boundary, right? So uh, the way that this, sorry, the way that this would be represented would be different. Sorry, my bad. Let me just erase this. Let me just draw a better sort of way for you guys to get it. So um, so if you guys want to look at like this line would look something like this. So this decision boundary would look something like this, right? And assume that you have, let's just say, some sort of 0, 0, 0 here, and you have some sort of x here. Okay, so this line, if you look at it, is actually represented by this this formula. So you can think of this as sorry, theta 1 x1 plus theta 2 x2. Yeah, so this you can think of it as x1, and this you can think of it as x2. And when you represent the decision boundary, the line which is represented by this equation, this on this side you have a different result, and this side you have a different result. So you can take that linear regression concept and you can twist it around to make a decision boundary when you're looking at logistic regression. Now, okay, going back to the slides. Okay, so suppose we are the example of where we can use this, right? So suppose we are a bank, okay, and we want to find out which credit card transactions are legitimate and which are not. This is a classification problem again, and it's very binary. There's legitimate and there's not legitimate, and you can use logistic regression for that. Obviously, you wouldn't be very successful with logistic regression on this. I don't think so, but that's a different story. You can use it, right? The other thing is, suppose you're investors. Investing is not just looking at the predicted stock price in the future. You can also translate a stock price prediction for tomorrow into just a decision for today. So the decision for today is, do you buy or sell? And that's a very binary thing. And again, you can use linear regression to sort that out. Now, so the third thing is, yeah. So, anyways, so the third use case over here is clearly a terrible use case because that's a regression problem. That's not a classification problem. So, yeah, moving on.
Rama, so I have a question. Is it only possible for two criteria? What if it's more than two possible?
Sorry, yeah, more than two is actually possible with logistic regression, and we'll come to that later in the thing. So it's a
Okay.
bit messy, but yeah, you will see that it is possible. Yes.
Okay.
For multiple classes, right? Typically, you would end up using a neural network, but that is for next week. So yeah, for this week. But anyways, you can actually do it with multiple classes. But the only thing actually you do is, okay, I'll just kind of spoil it here, which is like logistic regression is X or not X, right? Now, if you had like 4 classes, you can do X or not X, Y or not Y, Z or not Z, and say A or not A. And then remember what we talked about in logistic regression is a probabilistic result. So the probability you get, you're just going to look at which one gives you the highest probability. Does X have the highest probability, Y, Z, or A? And you will just assign that class to the values of the to the data that you get. I hope that makes sense. Does that make sense?
Yeah, that makes sense.
Yeah. Okay. Anyways, so how can it be represented numerically? I think we covered this. You can represent success as 1, failure as 0. You can actually represent success as 1, failure as -1, anything like that. So now the thing is, if you want to make it a probability or probabilistic sort of function, right? We need to have some way of squeezing those outputs. So, for example, if you have a theta 0 into x1, sorry, theta 0 plus theta 1 into x1 plus theta 2 into x2, what you run into is like you can have like all sorts of numbers and stuff like that. But how do you squeeze that into a 0 to 1 probability? And that's something that you do with this function that is called the sigmoid function. So the sigmoid function is generally we denote the sigmoid function by by this notation. So g of x, generally you'll see g as the function denoter, and it's given by this. So it's basically e to the power of minus x divided by 1 plus, wait, is it? No, I think it's e, wait, no, wait, 1 second. Nah, let me just stick to the one that I usually use. So 1 by 1 plus e to the power of minus x. If you multiply e to the power of x, oh yeah, this is the same thing as e to the power of x divided by 1 plus e to the power of x. Yeah, anyways, so the main thing that we'll be sticking to for this class will be the top one, so I'll just remove this since it's unnecessary. Now, anyways, yeah, so this is the sigmoid function, and what this does is it actually works to squeeze the values you get into a 0 to 1 probability function. So think about it in this way. So okay, I think x was a poor choice of letter. Instead of x, I think I will go with z. Okay, my iPad is hanging for a second. Okay, yeah, okay. So let's just call it z. Okay, so if z is a very high value, then e to the power of minus z, then sorry, you know what, then minus z goes down, therefore e to the power of minus z uh, goes down as well. So if this happens, then you have 1 plus e to the power of minus z also going, I mean also, yeah, also going down in value, and that means 1 by 1 plus e to the power of minus z, because again, remember, you're making this the denominator now, therefore this should increase in value because the denominator is decreasing in value, therefore the whole thing should increase. And remember, this function is supposed to give you the probability, the 0 to 1 sort of squeezing to give you a probability. And intuitively, if you have larger values, you will go towards 1. And in the opposite direction, if you were to have smaller values, that is more negative values for z, if you have really negative values for z, then e to the power of minus z will be a very large number, right? If z is a very negative number, e to the power of minus z will be a very large number. Okay, so anyways, so if that's the case, then 1 plus e to the power of minus z becomes a very large number, and therefore 1 by 1 plus e to the power of minus z becomes very small. So you can see that if you get more negative with z, you go towards 0, and if you get very positive with z, you go towards 1. And that function it represents itself like this. So if you have, so you have this sort of yeah, okay, so you have this sort of function, and you notice that if you wanted to get 1 by 2, which means a 50% or 0.5%, sorry, 0.5 probability thing, right? How would you get 1 by 2? 1 by 2 for 1 by 1 plus e to the power minus z, that means that the e to the power minus z has to be equal to 1. Is that correct? Right? And if e to the power minus z is equal to 1, that means the z has to be equal to 0. Right? So if you see over here in this graph of z versus g of z, when the z is 0, you have this 0.5. This is the point where it shifts to the other class. Okay. Now now you must be thinking, right? If this g of z function is like this, how do I move? How do I manipulate the z over here? If I were to use the same thing for every classification problem, what's the difference between any classification problem? And the answer to that is we in fact mold the z in a way that it suits our classification problem. So what I mean by that is this z over here. So when you have okay, I'm just going to write over here. So the z over here is in fact our hypothesis function. Okay, so we have a hypothesis function which is similar to the linear regression thing, which is like something like theta 0 plus theta 1 x1 plus theta 2 x2 plus how many other features that we have, right? Plus theta n xn. So now this z is a function of x, right? And theta. And um, yeah, so basically we construct the z with these values, with these values that we have from our data set. And then the squeezing function squeezes it between a probability between 0 and 1. So now the question is, right, what we want to do here is we want to optimize this problem. So we have a function over here that does seemingly what we needed to do, which is squeezing it into a probability situation. And we have the function to sort of construct the z. So now um, the question is, how do we optimize this problem to find the right sort of weights? That is, we need to, over here, the x1, x2, and everything is given to you. X given. Now, the only thing that we really need to find and need to mold is theta. Theta is the only thing that we need to mold, right? So, how do we mold that theta? And let's get to that. So again, as you can see over here, the way the function is drawn, you see that at the 0 point, you switch over from 0.5 to greater than 0.5. Yeah. Uh, so the the good thing with the probability thing is that, you know, if you have like a classification problem that's very binary, and imagine you're trying to like let's say you're trying to you're trying to you're trying to say, let's talk about the cancer thing itself, right? You're trying to decide on a course of treatment. um Imagine if someone gave you like a diagnosis of no cancer when you have something like 0.49 probability of having cancer. That is 0.49 is quite high, and you'd like to know that, right? And you'd like to chart sort of an advisory sort of course of treatment. You'd say, for example, come back in 2 weeks, come back in 3 weeks, we'll check again, we'll check this, we'll check that, we'll do some more tests. So probability is quite important, and it's quite a good way of going about these classification problems. um, yeah, so as you can see over here, we're just taking that the linear regression function, and we're going to put it into this classification problem. So sorry, I may have made a mistake in uh, using I made a mistake in using this as the notation for this. So in logistic regression, let's just call this something else. Let's just call this uh, yeah, let's just call this like k theta of x or something like that. Yeah. So the h of theta, I'll just go on to the new page. So the k of theta of x is equal to theta 0 plus theta 1 x1 x2 blah 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 blah. H theta of x is equal to 1 by 1 plus e to the power of minus k theta x. So yeah, so this is basically a hypothesis, because remember, our hypothesis is the value we want to output, and we are trying to output that probability. I'm just gonna put this intuition in your head from now, okay? So you know how when you're looking at questions in like in your high school and stuff, right? They talk about p of y given x, and sometimes I don't know if you guys really process why you need to do that kind of thing. In this case, this is actually one of those problems. So this is literally the hypothesis is just trying to look at p of y given the inputs x. Okay, so just keep this in mind. We'll come back to this, circle back to this concept later. So this is what this is. So okay, so the same principle remains as we talked about earlier. If you have really negative numbers or values of z, sorry, if you have really negative values of uh, theta transpose x, in this case you look at it is written as theta transpose x, right? So if you have really negative numbers of theta transpose x, the exponent becomes very positive, and therefore the probability becomes very low. If you have very high theta transpose x, it's the opposite effect. So now we're looking at what cost function do we use, because all of these are optimization problems. We're trying to optimize and find the theta value that's the right one for us. So looking at this, we defined the cost function for linear regression before as this squared error that we looked at, right? We looked at the difference between the actual value y and the hypothesis function. Now, obviously, that is a bit that's a bit difficult to use over here, in fact, because well, first of all, it, we're giving outputting a probability, right? So um, when you're outputting a probability, it's a bit different. So it's like, for example, you would want to penalize some things more than others. So for example, if I gave you a certain diagnosis, right, that you didn't have cancer when you actually had cancer, uh, that would incur a higher penalty than, for example, giving you a 50% output. That should have a disproportionately higher penalty than if you just had like a 50% result that came out. If you had something that swung completely the other way, something that told you that you have like 100% cancer when you actually didn't, we would want to give you a greater penalty than if you just gave outputted a 50% result. So this squared error function isn't the optimal way of going about it with logistic regression. We want to penalize complete mislabeling a bit more than we want to penalize inconclusive results. So how we can do that is adapting the cost function in this way. So the cost function over here, if you look at it, right, is okay. So let me just step you through the entire cost function, right? So first of all, the cost function that you see in the second one here, the first thing is the summation 1 to n. The summation 1 to n is for all the training examples that you have, okay? So the training examples, you have n training examples. We're just summing up the errors for each of them. Now, 1 by n is to average out that error. We discussed this last week, if you guys remember. So yeah, we're doing the same thing that we do with linear regression in terms of averaging out the errors from n data points. Now let's look into the summation, right? So into the summation, we have y. Let's just ignore the I, right? Let's just look at the I refers to each training example. Let's just look at it, one isolated training example. So instead of yi, I'm just going to say y. Instead of xi, I'm just going to say x. This obviously replicates for each of the training examples. Now, if you look at the y into log h theta of xi, right? This makes sense in that. Okay, so this makes sense in that if you have a okay, if you have a class that is 1, okay, not 0, 1, a class representing 1, you only want to calculate an error term related to that 1. You do not want to calculate an error term related to the 0. The issue with the probability sort of thing, right, is that when you're getting the probability, you're calculating the probability of the one class, okay? So when you're calculating the probability of the one class, you are in fact not, I mean, you cannot take that as the probability of the 0 class. The probability of the 0 class is 1 minus the probability of the 1 class, right? So obviously the way you calculate these error functions differs based on what the output is. If the output is 1, you will calculate the error function differently than if the output was a 0, because the probability that we are giving is different. So for every, I'll repeat myself, for every probability that we give, it's a probability that it's the class 1. The probability that it's the class 0, for example, is 1 minus that probability. So we treat it a bit differently. So let's take it step by step. Let's look at each individual thing in this. So there are two main individual terms. That is yi into log of h theta xi. Sorry, I should stop saying I. So y into log of h theta x, that's one term. Then the second term is minus 1 minus y into log of 1 minus h theta xi. Okay. Uh, okay, I think I may have made a mistake over here. I think it's supposed to be plus 1 minus y. Yeah, I think it's supposed to be plus 1 minus y. So my bad on that. Yeah. Anyways, so let's just ignore that for now. So let's look at the first term that I talked about, which is yi into log of h theta x. Sorry, y into log of h theta x. When I say log, you can just think of it as ln. Okay, let's just take it as ln so that you have the exponent sort of clear, right? The base exponent. So okay, so so this yi log h theta x, it deals with cases where y is 1. So when y is 1, this is activated. When y is 0, the output is 0. This part of the error function is deactivated, because if y is 0, the whole y into log h theta x, that whole term is deactivated. It becomes 0, so it's nothing. But when y is 1, this term is activated. Now similarly, if you look at the other side, which is 1 minus y into log of 1 minus h theta x. So in the 1 minus y into log of 1 minus h theta x, you see that term is activated when y is equal to 0. When y is equal to 0, 1 minus y is equal to 1, and therefore that term is activated. When y is equal to 1, 1 minus y becomes 0, and therefore that second term cancels off as a 0, right? So now we have two separate terms calculating the error for two separate cases, and we have put them in the same formula. Instead of making an if-else statement here like, oh, if y is equal to 1, then you calculate the first term. If y is equal to 0, then you calculate the second way. Instead of that, we put all of it into one function, right? I hope you guys see that. Okay, so um, now let me, after this, I will. Okay, so the other thing is, the reason why we have the negative over there, right, is because, and the reason why I said that it should be plus 1 minus y into log of h theta is because when you have ln of these numbers between 0 and 1, or the log of these numbers between 0 and 1, you get negative numbers, right? You get negative numbers when you do the ln or the log of these things. So to remove that negative sign, we do a negative 1 by n outside. Okay, I hope that's clear. Anyways, we will move on to, so as I talked about earlier, that y and 1 minus y, the purpose is that we're looking at the two possible outcomes and the error that comes with them. Okay, so what is the intuition, right? When you think about it, right, is I've shown you here, okay, I should have probably used a ln function, but okay, I've used the log function and the ln functions in a very similar way. So here you can see these two sort of results. So the first one is the log of x, right? Now the 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 x in this case, you should picture it as your hypothesis. Now assume that your hypothesis comes out as 1. Okay, remember that the log of h theta x is activated. Log of h theta x, wait, where is it? Yeah, log of h theta x is only activated when your y is 1. Log of 1 minus h theta x is activated when your y is 0. So let's look at the log of h theta x. That is activated when your y is 1. That is the red function. Okay, when y is 1, okay, and your log of h theta x is 1. If your log of h theta x, remember that the x-axis is basically over here. That is the log of, that is the h theta x. Sorry, that is the log of h. Sorry, one second. Okay, sorry. Yeah. So the x-axis here is represented by h theta x. X is probably a poor choice of words here, because you know it's the x-axis and I'm saying h theta x, but you get the idea. So if your probability is 1 and the result is 1, the error over here, when you look at the red function, which is represented on the error is represented on the y-axis, is 0. But if the actual value was 1, and then your error was, sorry, your probability, the output you gave was 0, look at the error. The error is nearing infinity, right? It goes up and up and up. So the whole idea is that if you have a 1 class and we give you a 0 probability, we want to penalize that maximum. You have completely messed up. So that is the idea of the red function. The red function is activated only when the output is 1. Now you look at the green function. The green function is activated when the output is 0. And you look at the log base 10 1 minus x, right? So when you look at log base 10 1 minus x, it's a similar thing but the opposite direction. So if your output is 0 and you get a probability interpretation of 0, the error, which is represented on the y-axis of this graph, is 0. You get a 0 0 that matches. That's great. Your 1 minus h theta of x is 0 and your actual thing is 0. So therefore we're happy. But now assume it's the other way around. Assume that we give you an output that is 1. So if we give you an output that is 1, then we want to penalize you highly because the actual value is actually 0. So yeah, you've completely messed up on the prediction. So therefore we penalize it, and the penalization goes towards infinity. So these are the two functions you see. The red function is for when the y output is 1. The green function is for when the y output is 0. So I hope that registers. Does anyone have any doubts about this? Um, anyone having a hard time comprehending this? Anyone want me to go through something specific? Okay, I see some shaking heads. So
Is this something related to entropy or something? Because it just reminds me, but I can't. But I'm not really sure about that.
um, well, depends on what you mean by entropy. But I don't think this is a concept related to entropy. I'm not sure. Anyways, I will get back to you on this later. But do you get the idea of the concept of penalization that works here with the error function? That is the main point. Do you guys see that? Well, okay, I see some nodding heads. So
Wait, sorry, why do you choose log again?
so the property of the log function is that it disproportionately penalizes stuff on the wrong side, and it smoothens out once you get closer and closer to the prediction. So we don't want to linearly penalize. We want to penalize in a way that's exponential when you get further away, and is not plateauing when you get closer to the prediction. So that is why we use the log function. The
Okay,
other,
okay.
sorry, yeah.
Then how does this relate to the Sigmund thing?
So the sigmoid function again, that is what gives you the hypothesis. So when you look at this, the h theta x, right, that is what you get through the sigmoid function. The sigmoid function is so the sigmoid function here. So basically, this hypothesis here is that it takes your k theta, okay, and then it passes it into the sigmoid function. So this is basically g of k theta of x. Remember, g is the sigmoid function, right? So we are taking your k theta of x. We're looking at how negative or how positive it is, and then we're using that to squeeze it into a probabilistic interpretation. Now we want to so now we have some sort of initial weights that we're using for the system that we have. We have some sort of initial weights. We take some initial weights. Okay, there's a way to get better initial weights so that your optimization process is not that long. But I don't think we're going to cover that in this course. Maybe you guys can look into it. So how to set the initial weights of any system. So, but anyways, the point from once you have the initial weights is we want to optimize this in a way that minimizes error in some way. And now we're trying to define that error. And the way we defined that error was with that ln function and penalizing extremely wrong classifications worse than slightly wrong classifications.
Okay, so the sigmoid and the log function are like two different things, is it? Like
Yeah,
they're not. Okay,
yeah.
okay.
The sigmoid gives you the probability, and the log functions over there, they give you the error. They are the way we optimize the,
Penalty.
yeah, they are the penalty, and we want to minimize the penalty. That is our optimization problem. That's when we use the calculus to determine the theta weights that we have. So
Okay, okay.
that is determined by optimizing that error. That is minimizing that error.
Okay, thank you.
Yeah. Okay. The other alternative is something fairly simple, which you can optimize for. So you can just total up the incorrect classifications, right? But that wouldn't be fancy. So yeah, we do it this way. But no, I'm kidding, right? So it really depends on your type of problem. So this is something else that you guys should really look into with classification problems, right? You guys should look at the penalty you should attach to each wrong classification. So um, I can think of certain things where, for example, you would attach a penalty more strongly to something than something else. So, for example, right, in most cases, false positives are better than false negatives. So, what do I mean by that? For example, let's say that we're testing for COVID-19. Assume that when we do tests for COVID-19, right, assume that we were running a machine learning program on the person, okay? this is impossible to do, but or maybe this is possible to do. So for example, you take some sort of gene sequence from the person or whatever it is, some sort of bio data from the person, and then you try to run a machine learning algorithm, right? And you try to predict whether they have COVID-19 or they are likely to develop the COVID-19 or whatever. Okay, it's detectable in a few days or something like that. Now, if we were to false detect that they do have a chance of developing COVID-19, and then we take extra precaution, that error, that should not be penalized as much as, for example, saying that the guy will not get COVID-19 and he ends up getting COVID-19. That should be penalized more, right? So the optimization problem, which is the whole crux of this whole thing, what is our optimization problem and what are we optimizing our weights for? That should be defined in a proper way, depending on your problem. So when I just told you about the whole thing, so for example, if I were to give a 0%, this guy develops COVID-19, I'm giving him a 0% chance and he gets COVID-19, I want to penalize that much more than I do if I were to say he confirmed gets COVID-19 and he doesn't get COVID-19. I want to penalize the first case much more. As opposed to what I was just talking about with this function that we're just talking about here. This function here, we are penalizing wrong classifications either way in an equal manner. So we are penalizing both sides of the wrong classification. If you look at here, if you in the red function, if you were to give a prediction of 0 when the actual value is 1, we're penalizing you infinity. If you were to give a prediction of 1 when the actual value is 0, we are also penalizing you infinity. Now, this might not be the case for many optimization problems, like the COVID-19 case that I just gave you. So false, generally, when you look at things, false negatives are worse than false positives. So yeah, these are things you should probably think of when you're looking at your optimization problem. Yeah. So, Hans, do you get the point about?
Yes, yes. I think it's a lot clearer now.
Okay. Happy. Thank you for asking. I hope it's clear to anyone else who had questions as well. Okay, so the other way of obviously doing it is simpler, which is just totting up the number of incorrect classifications. This is basically looking at your probability. Say you were getting 0 to 0.5, you just round up and say you had a 0 classification. Now assume that was actually a 1 classification. We would just say, oh, that's one wrong thing, and we just add it to the total. So we define an optimization sort of equation for that. So that's another case where you could do it that way. This is in cases probably where a wrong decision isn't the end of the world either direction. It's fine. So we're not yeah. So anyways, so the question is, how do we get the right parameters and how do we sort of optimize this problem? So yeah, so anyways, so this sorry, one moment. Sorry, 1 second. 1 second. Have I got the graphic? Is it do I have the graphic here? Yeah, so anyways, I do not have the graphic. Never mind. So in these cases as well, your optimization problem is like this, and similar to the last time, I'm not going to work through the calculus because the calculus is quite complicated, but eventually you derive this sort of equation, which is the same thing as the last time, where you modify your theta parameter, the weights, in a similar way. So this equation that you see on the screen here right now, that was what you used for linear regression as well. And the way the sigmoid function works out, that you can use this for the logistic regression problem as well. So you can, when you optimize it, you do your modification of your weights, your theta j, for each of the j values, I mean each of the thetas, and you get to the bottom of the valley, the gradient descent, right? I'm not going to step through the calculus because, again, the calculus is complicated and you guys, a significant number of you are year ones. So this is something you guys can look into. So the calculus of logistic regression gradient descent. So this is something you guys can look into. Okay, so the pros and cons of the system is, yeah, output in probabilities. It's useful for further statistical analysis. Uh, a probability can be interpreted as a prediction. So this is understood much easier, right? If I were to just say 97% chance of this, that's kind of nice, right? It's kind of nice to hear, as opposed to you just hearing a binary this or that. I feel this is better, right? So you can be as cautious as you need to be, or as it can be a more how do I say this, aware of what to do. Um, Now, the disadvantage comes when you're talking about multi-class classification. And again, we talked about this earlier. Someone asked the question. It was a very good question. What do you do when you have 3 or more possible outcomes? And in those cases, we make models for each outcome. So X or not X, Y or not Y, Z or not Z. Sorry. Yeah. So you make you do 3 models like that, and then you see the probability that you get for X. You get the probability, see the probability for Y, and probability for Z. Whichever has the greatest probability, you assign that class label to it. See, the other thing is, this is very difficult to do in 3 class if you're doing it in one straight way, because uh, now when you have 1 and 0, the reason why it works is because it is binary. It is so this or this, that sort of thing, right? If you had 3 classes, you couldn't do that, because again, we're squeezing it between 0 and 1. We're giving probabilities. That's one thing. So we're already talking about something or not something. If you were to do if you were to move it to 3 classes, you couldn't fit it within 0 to 1. That wouldn't make sense in any way. So yeah, it just does. It's not possible to do in one straight go. Um, like the joke I showed you guys earlier from Silicon Valley. Yeah, one of the models could be hot dog or not hot dog. The second would be baked rice or not baked rice, and third one could be pizza and not pizza, and you could classify things that way. So maybe that in that video clip that I showed you, maybe they could actually get a pizza classification if they tried. Yeah. So now we learned about bias and variance before, and the same thing applies in logistic regression. If you have fewer sort of features, fewer x's, you have fewer theta values. That means you have fewer knobs to play around with. That means that there's underfitting of the graph, or tends to be underfitting of the graph. If you have too many knobs to turn around, that is like too many theta values, too many x values, therefore too many features, too many theta values, you can overfit the graph as well. And something you guys can ponder over is what that looks like in logistic regression. And I can kind of give you the idea actually right now. So let's just say that I were to draw this sort of thing here, and let's just say sepal width, petal width. Let's just say that the relationship between these two, right, is like uh, okay, it's like this. So let's just say that you have some sort of complex uh, yeah, complex thing. Okay, so let's just say it might even go something like this. If you have two complex how do I draw this? Okay, this is actually quite difficult. uh okay, yeah, something like this. Basically, you have a really complex boundary. I hope you guys get it. Right now, for some reason, I cannot draw it out. I don't know why. It's a bit tough to get it right. But anyways, you get the idea. If you have too complex a model, sometimes you can overfit to the data, and it doesn't reproduce when you go into the test case. Sorry, when you go into the testing data. So that's the whole point about variance, the possibility of overfitting. Okay. Now we now okay. I didn't expect it to go this long. In fact, I thought we'd end earlier today. But anyways, so yeah, anyways, let me just continue through this. Anyways, yeah, so yeah, we have training data, cross validation data, and testing data, right? So we talked about this in the first, like in our first lecture together. And the cross validation data I told you is something which is kind of testing data but not quite testing data. So for example, we don't know which model to use, right? And we're kind of confused about which model to use. So what we do is we can try to use each of these models on the cross-validation data. So first of all, we train these models, each of them, in the training data. We train each of them in the training data. We optimize those data parameters, and we get the best sort of case of each of these models. Now, what we use the cross-validation data for is to test or to find out which of these models do we actually choose. We've already optimized the theta for each of these, but now which model do we choose? And when you think about it, right, the cross-validation data actually helps you train another parameter. It helps you train the parameter which is the number of features that you use. When you think about it, the degree of complexity of the equation. That is what is trained by a cross-validation data. Now, once you've trained anything using your cross-validation data, once you've even touched it that way, your cross-validation data is tainted. It gives you a more rosy picture of things than they ought to be. So therefore, you need that testing data still at the end, where you can check out if your model has reproducible results in the general case. By the way, the H theta x over here is the linear regression one. The only difference when you have logistic regression is you just wrap it around with a sigmoid function. So you would have a g of H theta x. Okay, so yeah, as I just talked about, the extra parameter that you're actually optimizing for over here is the degree of the model. So that's quite cool, right? And you're actually tainting the cross-validation data, and therefore you cannot use it to show your peers or whatever, hey, my model works, because it's a rosier picture than it probably ends up being. Okay, so I'm not going to drone on too much over this because it's not something that you've used particularly much. When we talked about regularization the last time, regularization, which means in your function, you basically add a bunch of theta j square values. So once you kind of add this theta j square to this function here, you automatically, when you're trying to minimize the value, you're trying to your theta values will become minimized. We discussed this in the linear regression lecture, and you guys can revisit that, and you guys will see that you guys should note that it's the same case with logistic regression. You use a similar lambda theta j square so that you don't overfit as much. You reduce the theta values. Now, let's just think about diagnostics. The next thing that I want you guys to think about is diagnostics, because oftentimes you will see that the results aren't showing. You aren't seeing your results, right? And you'll be wondering, why aren't my results showing? What can I do to fix things? So if you see that it doesn't work, right, what is what might be the first thing that you guys do? And maybe someone can sound off and tell me what they think they do. Yeah, what is the first thing you think you guys would do if your model's not working? What is the first thing that you think of? Well, okay, so there's a lot of things that you could do if your model's not working, and it's not always just getting more training data or getting more features. Okay, it certainly isn't always getting more features. It could be getting more training data. Getting more training data doesn't ever hurt your cause. Getting more training data almost always will help your cause, but it depends on what degree. And also, getting more training data is expensive, and it's time costly, and it's also money costly in many cases in industry. So, okay, crap. Yeah, okay. So, oh my god. Okay, wait 1 second. Let me just switch off my notifications. Yeah. Yep. Sorry. Yep. Back. Anyways, let's. Yep. I think you guys can see my screen again. Yep. Looks good. Okay. We can resume. Okay. So, as I was just talking about it, right? So training data never hurt your cause, but it's a question of which gives you the best bang for your buck. And so these are some things that you guys can think of. So the solutions to when you have facing a problem with your model is that if your issue is high variance, in that your model gives you low error on your training data. Like it works perfectly well for your training data, like too well almost. It just works so good. But then for the testing data, it doesn't work well at all. Okay. In that case, we would advise you to get, I mean, the advice is to get more training examples. That fixes your high variance issue, the high overfitting issue. If you have too much variance, the other thing you can try is to actually reduce your set of features. And reducing your set of features makes the function less complex. And therefore, it's less fitted and less tailored. And therefore, it fixes high variance. Now, if you add features, it does the opposite. It fixes high bias in the sense that your model's too insensitive. You need to have something that's more customizable. That's when you'd add the features. Now, adding polynomial features is another thing. Adding polynomial features means you cannot actually bring in more features. You are limited to your number of features. You have x1, x2, x3, x4. You cannot get an x5, x6. So what you would do is you would combine the features that you have. You would combine it pairwise, maybe x1 into x2, x2 into x3, that sort of thing. And you use those as features as well, or x1 squared, for example. So this is another solution that you can have, which is adding polynomial features. Now, the other thing you can do is decreasing your lambda, which is in the case of regularization, right? So if you're using that sort of the lambda theta j squared term to sort of fix your variance issue, reducing that lambda fixes any sort of underfitting, and increasing the lambda fixes high variance. I think that's kind of intuitive with the equation. Okay. There is a way of doing this, and that is to measure sort of the bias variance. You can measure it using sort of a graph like this. So
Hi Rama. Actually, the methods of fixing the bias and variance, like it doesn't really, like there's no difference between linear and logistic, right? Because both also kind of like employ the same methods.
yes, that's accurate. Yeah. Yep. Okay. So yeah. So basically, what you can do in these sorts of things is you can actually plan this sort of map this sort of. So you can sort of put training data here, and you can put like sort of what is it, error here. And generally, what should happen is your testing error and your training error should sort of converge. Should sort of converge to something like this. So this is the sort of common, or rather, in some sense, ideal scenario where so the whole idea of this is you guys should really, I mean, kind of chart this out. And obviously, when you're doing these things, when you're actually working on projects, you might not chart this out exactly, but the intuition is important. So the intuition here is that you should actually look at whether your extra training data would actually make a difference, or if for example, even with the extra training data, nothing's happening, it's not converging to that sort of value, your test error is still high, that's when you know that the extra training data doesn't work out. And that's when you look at alternative solutions. The goal is also to make sure that this convergence point, right? The convergence, when you call it the limit, right? The limit, in a mathematical sense, you call it the limit, but you want to make sure that converges as low as possible. What you do not want to do is fixate on this error. Do not fixate on this, because this is the important one. So you want to fixate on this. So you want to look at this. Yeah. The whole idea of this is that once you get more training examples, you should see a decrease in the testing error. And the whole idea of the training data is if you have a fewer sort of training examples that you've seen, then you can probably tailor your model to fit it exactly. Therefore, the training error will be very low at the start. Once you get more training examples, with the noise that you have in your data, the function becomes very complex. And once you get too much training data, your function cannot perfectly fit it as much. Therefore, the error keeps going up slightly. But once you get to a certain point, your function is your function, and that's why the convergence happens. Yeah. So yeah, to summarize, right, almost anything can be transformed into a classification problem. So we just talked about the stock price prediction thing. So you have linear regression with stock prices, and you would probably think, oh, I predict the stock for tomorrow, Apple stock tomorrow, 150 something dollars, whatever it is, and you predict it for the rest of time. That is your time series job. But look, this sort of thing, this determines, for example, you can transform it into a buy or sell decision. Or a whole decision or something like that, in which case you would probably use multi-class logistic regression. Yeah, so we've also looked at multi-class regression and how it's possible. We've looked at bias and variance and how we need to take it into account, and how we sort of modify our model and the way we go about stuff based on what we see, whether we see high bias or high variance. So we've looked at a few possible solutions to each of those. So we've also looked at what cross-validation data is useful for. I've told you why we have cross-validation data, and why it becomes tainted upon use, and why we need to still have the testing data at the end. So the food for thought is, what if your negative class, I promise this is the last thing, but it's a bit mathy, so yay. But anyways, so what if your negative class was -1? So what would you do in that case, right? So instead of your negative class being 0, what if it was -1? So then how would you go about looking at things? And let me just show you sort of a derivation that you can do, which is very simple. In fact, for those of you who've done even high school math probability, this one should be understandable to you guys. So keep in mind, as I told you earlier, what we're doing with this probability thing is giving out a P of Y given X. I told you guys to take note of this earlier in the class so that we'll circle back to it at the end. So when we give out a probability of an output, we're giving P of Y given X. Now, assume that the data is not time series data. So assume that your XY combinations are independent. So for example, if I have a set of inputs and then output, inputs, output, input, output, a bunch of training examples like that. Now assume that each of these are independent. And if they're not time series data, generally they should be independent when you think about it. Only if they're time series where there's a knock-on effect and all of that, that's when you have dependency. Assume that it's independent. Now, our goal is to make sure that P of Y given X is high for all the training data instances. Now, obviously, what we want to do is to get the testing error to be minimum. That is the ultimate goal. But as someone who is learning from the training data, what we want to do is to also try to fit it to the training data. That's the primary objective. We're trying to fit it to the training data, but we're not trying to overfit it. Now, keep in mind that we're trying to fit it, right? So what we're trying to do is to maximize the P of Y given X for all the training data instances. So therefore, for any X given like this, we will get that Y. So that is what we're trying to do. So, okay, so when you look at it this way, right? The second last equation that you see is P of Y1, Y2 all the way to Ym, given that you have X1, X2 all the way through Xm. Now, this basically what I'm saying here is that the probability that all of you get Y1 given X1, the probability that you give Y2 given X2, all of these combined, that is what the left-hand side notation is. And what is this equal to? Keep in mind that each of these cases, P of Y1 given X1, P of Y2 given X2, all of these are independent. I made that very I stressed on that very clearly, that these are independent. And if you have independent probabilities, the ability to combine them, to see that all of them happen, is by multiplying them, right? Because they are independent. So you see this left-hand side is equal to P of Y1 given X1 into P of Y2 given X2, and so on and so forth. Keep in mind that your probability that you get a yi, any y, given x, is given by that sigmoid function, okay? So let me just take this, and let me just go and let me just show you something cool, right? So you have P of yi given xi is equal to g of yi weighted p. So keep in mind over here, right? What is the intuition here? Remember what I told you about the sigmoid function. If you pass in something super negative to the sigmoid function, you will get a very low probability. you pass in something super positive to the sigmoid function, you will get a very high probability. Now, keep in mind, in this case, we were talking about how we are looking at two classes, not labeled 0 and 1. We're talking about two classes, 1 and -1, right? Okay, wait, sorry, okay, yeah. So, y1 or -1. So, what is the logic behind this? Keep in mind, if neg, then low, if pos, then high. So the probability is high if it's positive as hell, and if it's negative, really negative, then the probability is very low. Now you have the 1 or -1. Now, if your prediction is super positive, and your value you get is 1, then the combo of these two, the product, which is what is here, the product will be positive as well. If this is negative, so this is -1, and this is super negative, the product you get will also be positive. And now, if you look at this, both these cases that I just talked about are correct classification cases, where the actual value is, if it's negative, your output is also negative. Your actual value is positive, your output is also positive. So therefore, we want it to be positive. We want this to be a high probability. We want this to be rewarded. This is what we want. But if we have a mismatch, so for example, if y is positive, so that means 1, and we see the theta x is negative, the product we get is negative. Similarly, if this is -1 and the actual output that we predict is positive, then the product is negative. And if it's negative, then the probability is low. If it's positive, that is the correct classification, the probability is high. Now that we've established that, right? So remember what I talked about, where we looked at the product of each of these p of yi given xi's. So what we want to do is to maximize that p of y1, y2, ym given x1, x2, xm. So we have p of y1, y2, ym given x1, x2, xm. So this is what we have for the training data, and this is what we want to maximize. We want to make sure that our model gives each of these y's for each of these inputs. We want to maximize this. And remember, we just talked about it. It's p of y1, 1 given x1 into p of y2 given x2, p of ym given xm. So this is what we want to do, right? Now keep in mind that our probability is as we outlined over here, our probability is equal to this for each of these. So what we have here is a product. Remember that if you guys remember, this is a summation notation and this is the product notation. So yeah, I'm just going to remove this for now. So you would have a 1 to m. Sorry, I don't know why my iPad again is hanging a bit. Okay, yeah. So you have a product y. So remember, we're trying to multiply all of these, and it is I is equal to 1. So then we just say g of yi into theta x I, theta transpose xi. Anyways, so when you have this, right, you have the product here. Now, how do we make the product a sum? And how do we make the product a sum is we just use the ln function. So remember that if you have ln x plus ln y, that is equal to ln xy. So keeping that in mind, if we apply the ln function to this, so remember, we're trying to maximize this. We're trying to maximize this. We're trying to maximize ln of this. So we keep in mind we're trying to maximize ln of this. Yeah, so therefore what this becomes is maximizing a summation of I is equal to 1 through m of ln of g of yi times theta t xi. I hope you guys follow this.
Sorry, I just want to check, right? Xi here is a number or is it a vector?
Xi over here is a vector. Xi is a vector. The I is just denoting the number of the example because we have m training examples, and we're trying to optimize this by making our function such that this is maximized. We're trying to fit it to our training function, sorry, training data, and that is essentially doing the same thing as maximizing this. And the I over there is just denoting the number of the example in the training data. So it's the first or the second or the third to the nth.
So theta transpose Xi basically is a number that gives us the probability of the predicted probability.
The number that we feed into our sigmoid function. The sigmoid function squeezes that number into the probability. So remember what we just talked about here. If it is super positive, if you have a match that is y is positive and the theta txi is super positive, and it's fed into the sigmoid function, the probability you get will be super positive. Sorry, will be super high. And if there is a mismatch in the signs between the y and the theta here, sorry, y and the theta x, then you will get a super low probability. If you have negative, that is correct classification, you would still have a high value going into the sigmoid function. Therefore, you will get a high probability. That is what we want. So now we're trying to maximize this. Essentially, what we're trying to do is, okay, so then you can also say we're trying to minimize the same thing because we're putting the negative sign there. The reason we put the negative sign there is because when you have the ln, you get negative numbers. So yeah, so we just put the negative sign there. And yeah, so ln of g.
Sorry, just to confirm, the ln there is to achieve the effect that we want to penalize very, very wrong predictions, is it?
Okay, so in this case, that is not the desired effect of the ln. In this case, the reason we're trying to do the ln is to simplify this product notation that we have here. We're simplifying it into a summation notation.
So it's like a notational trick.
Yeah, it's a notational trick because, as you know, ln of x plus ln of y gives you ln of xy. So we're trying to play on this, and we're trying to convert it into a summation problem. Because when you think about it, right, when you're trying to do calculus, summation problems are always much more easy than a product problem, right?
Yeah.
So when we're trying to optimize this, remember we're trying to talk about cost functions here. So we're trying to minimize this. So this is again an optimization function here. So when we're trying to optimize this, we're going to be using calculus, right? And we obviously want to make it a summation function so that it's easier by the end. So now once we're up to this point, keep in mind that the negative sign, I can bring the negative sign in. And if I bring the negative sign inside, what is basically any sort of negative or sort of any coefficient to a ln function, you can bring it up as the exponent, as the thing that is inside the function. So this would just become, so again, we're trying to minimize I is equal to 1 through m ln of g of y okay, that's too many brackets. Okay, let's just say -1. Yeah, so this is the same thing as this. And when we really do that, when we really get back to that, it's 1 by, sorry, no, it's, what am I doing? right? And if you remember what a g of yi theta txi, this is equal to 1 by 1 plus e to the power of so this is equal to this. Now, if you just bring this down here, then you are trying to minimize, just to bring that back, I is equal to 1 through m. Remember, you're doing over here, you're doing 1 divided by this, and this is equal to this. So 1 divided by 1 by this is just equal to this. So essentially, you have ln of 1 plus e to the power of minus yi times theta transpose x of I. So when you look at the function, this is what you're trying to actually optimize for. So let me just step you through it again. Remember that what we're trying to do is you want to optimize a function in a way that, given looking at the training data, given these x's, we want to get those i's that are corresponding to these x's in the training data. That could be written as a probability thing where we look at p of y1, y2 given all the way through ym, given the inputs x1, x2 all the way through to xn. If you were to do this, considering that these are independent independent distributions, these are independent sort of things in the data set, we can calculate the probability by just using the product rule and multiplying these together. So therefore we have this. Therefore we have this. So once we establish that, we look to establish what p of any y given any x actually is, and p of yi given xi is given by this. So therefore we just do this into this into this, and that is basically using this sort of pi notation to denote the product of g of yi theta xi. We use a ln to then make it a summation problem, which helps in calculus, right? And then once we do the ln thing, then once we use the ln operator, we have made it into a summation problem. After that, it's just mere simplification, and then you end up at this. We're trying to minimize this, and that is our optimization problem. Anything in machine learning actually just ends up becoming an optimization problem. And on this, you can just do some calculus, and then once you do your calculus, you adapt your theta weights, and you have your theta weights that help you with your classification problem. So this is a case where you have y is equal to 1 or y is equal to minus 1, and you can use this sort of method of doing things. Yeah, I hope that sort of was a nice sort of mathematical thing for you guys to see. For those of you who got it first time, bravo. For those of you who got most of it, nice. And I hope you guys can look through the recording to look at it again later. Okay, yeah, okay. So I have been recording, thankfully. Yeah. Anyways, that brings me to the end of today's presentation. Woohoo. Yeah. So thanks for listening. The other thing I just want to remind you guys about is the project submission deadline. It's really, again, I just want to stress that we're not looking for too much. We're just looking to see effort, we're looking to see commitment, and we're looking to see exploration. So we're not looking to see results. Again, if you're expecting us to see some sort of like crazy accurate figure, no, that's not what we're looking for. We're just looking for effort. And yeah, hopefully we see it. And the deadline for it is October 3rd, 11:59 p.m. That's a Saturday. The next thing that's coming up is on Thursday. On Thursday, we have the resume and internship sort of talk. So I think that should be very valuable to you guys. I'll probably attend it as well. I'm not sure. For me, I think there's some sort of clash with another sort of talk about an internship in Chile or something. I don't know if you guys saw the email on Outlook. So yeah, cool. I think I shared too much information there. Anyways, thank you very much for attending, and y'all can you can drop the call. Yeah, see you guys.
Thank you.
Thank you.
Thank you.